Hello and good evening everyone. As you know from the previous online seminar, my name is George Daniel from LC Patros and I am the online seminars team coordinator of EESTEC Challenge. On behalf of the EESTEC Challenge board and online seminars team, I would like to thank you and welcome you to the second online seminar. The lecturer for this online seminar is Ioannis Mytilinis, PhD candidate at the National Technical University of Athens. He will introduce himself later on. This seminar is held, as you know, in the context of EESTEC. And you may have heard in the previous online seminar that EESTEC is organizing this challenge. EESTEC is a volunteering European association that envisions all EESTEC students to reach their full potential in their academic, professional and social lives. The competition consists of local rounds and one final round. Local rounds will be implemented during March, and in the slide you can see the 24 cities that will organize them. The winners of the local round will be passed to the final round in May. The final round represents a live round. All the first winning teams of the local rounds will be competing for the winner of the competition by resolving the final task given by the company sponsor. This year the final round will be held in Novi Sad.
Hi all, I hope you're ready for an introduction to the Hadoop and Spark ecosystem. Let's take it from the start. My name is Ioannis Mytilinis and I'm going to present you the second online seminar for the EESTEC challenge on Big Data. If there are any questions about my talk, you can email me at gmytil@cslab.ec.ntua.gr. So let me tell you first a few words about me. I graduated from the National Technical University of Athens, where I studied electrical and computer engineering. After my graduation, I followed postgraduate studies at the Computing Systems Laboratory of the same school, where currently I'm pursuing my PhD on data management and distributed systems. During my PhD, I also worked as a research intern for IBM, and where I mostly did ML stuff, and then I got back to carry on my PhD. So, I'll give an outline of this talk. I know that in the first online seminar you were presented the WordCount application. We'll see it again, we'll discuss scalability issues about it, and we'll become familiar with notions like scale up and scale out. After that, we'll talk a little bit about some big data frameworks that are commonly used, and more specifically, we'll see the Apache Hadoop and Apache Spark projects. We'll discuss in detail their architecture and we'll see how to code in these frameworks, and we'll develop an application as a demonstration. So, as I mentioned, we will begin with the WordCount application. I know that in the first online seminar you were presented an example of it, but let's take it from the start. We are given a text like this, and we are requested to count the frequency of each word. That means that we need to count how many times each word appears. In our example, we feed this text to the WordCount application, and we get this histogram. In the horizontal axis, we have the words. I have plotted only the most frequent ones. And in the vertical axis, there are the frequencies. We can see, for example, that the word is the most frequent one, as it appears 4 times. We are ready to make a first centralized implementation of WordCount in Python. As we see in the figure here, the code is very simple and consists of only one function. In order to efficiently compute the frequencies, we use a dictionary that has the words themselves as keys and the frequencies as values. We read the text line by line, we split the lines by the space character, and update the dictionary accordingly. So every time we see a new word, we have to go to the appropriate position in the histogram and update its frequency. For the evaluation of our code, we ran an experiment on TripAdvisor data. TripAdvisor is a well-known site with reviews for different places of interest. In these two figures, we see our results. In both of them, in the horizontal axis, we have the input data size in megabytes. In the first figure, we measure running time, and in the second one, we measure memory utilization. We observe that both present a linear pattern. The bigger the dataset, the more resources we need. Here, we face a scalability issue. If our computer has only 4 gigabytes of main memory, for a larger input, our code is doomed to crash. So let's deal with scalability. If the resources are not enough, we have two options. The first one is the so-called scale-up. That means get a bigger machine. If my code cannot run with 4 gigabytes of memory, it may be okay if I buy a computer with 16 gigabytes. That has some drawbacks. The first one is that machines with high specs and specialized hardware are expensive. Not everyone can afford them. Moreover, if I have started the execution of my application and suddenly realize that I run out of resources, it is not easy to transfer it to a new machine without interrupting the execution. However, one good thing of scaling up is that the code remains the same. I do not have to re-implement anything, just run it on a different machine. The other scalability option is scale out. That means get more machines. One of the main benefits of this method is that it is based on commodity hardware that everyone can afford it. If I need 16 gigabytes of memory, I can have them by setting up 4 machines with 4 gigabytes each. Another benefit is that we can adjust resources on the fly. There is a bunch of literature work on adding and removing resources on demand. However, everything comes at a cost, and the cost here is that we need to write the code from scratch and develop a distributed algorithm that orchestrates these resources. The frameworks that we are going to see in this presentation are based on the scale-out approach. So, in this talk, we are going to see how to use scalable solutions for the processing of real big data. With social networks, IoT, and scientific experiments, there are many terabytes that are nowadays produced every day. But the question is, how can we handle them? One could say, keep calm and use Hadoop. Of course, apart from Hadoop, there's a whole ecosystem of projects where each is designed for a different big data case. The goal of this talk is to cover batch processing, and as such, we are going to focus on the Hadoop and Spark projects and on HDFS, which is the distributed file system that supports these frameworks. Batch processing on big data is based on a divide and conquer logic. That means that we divide the problem to many sub-problems or subtasks, where each of them refers to a different part of the data. After the computation of the many subtasks, the task that combines the solutions may be required depending on the algorithm. To put it in a funny way, consider this teacher that assigns 500 tasks to his student. Clearly, there are some scalability issues here. However, the student is familiar with the scale-out concept and assigns one task to each of his 500 friends. That is the way we are handling big data. We assign different subtasks on different machines. So let's start entering the Hadoop world. Hadoop is based on the MapReduce paradigm. But wait, what's this? MapReduce is not a system. It is a programming framework. It is a divide and conquer paradigm that we use to design scalable algorithms. It is very good for data parallel applications and of course needs a computer cluster to run upon. The first implementation of a MapReduce system was presented by Google in this paper, and open source implementation appeared right after, which is the well-known Hadoop. So let's see the structure of a MapReduce algorithm. We have an initial big data set, which is divided in a first step at many parts, and then we have the map phase, where many different workers, called mappers, are spawned to process the different parts of the input. In the second phase, called the reduce phase, intermediate results are combined accordingly to some logic in order to produce a final output. And clearly, this whole structure follows the divide and conquer model. So now let's see the Hadoop project. The architecture of the Apache Hadoop project consists of two layers. The first layer is the HDFS layer, that is where the data lives. And the second layer is the MapReduce layer, which is where computation takes place. Both layers follow a master-slave architecture. There are many slaves that either hold or process data, and one master that orchestrates these slaves. In this figure, we first see the architecture of HDFS, which is the distributed file system of Hadoop. The slave nodes are called data nodes, and the master one is called name node. When we want to store a file in HDFS, this file is split in blocks of equal size. The default is 64 megabytes, and every split is assigned to a possibly different data node. The name node keeps track of the mapping between the block IDs and their locations. For example, consider a client that needs to read the second block of a file. The client first contacts the master, i.e. the name node, and asks for a specific position within the file. The name node then finds out that this position corresponds to the second block and that this block is stored, let's say, on the first data node. The client is informed about the location of the requested block and directly contacts the appropriate data node. In this example, we can see a weblog file divided in blocks of 64 megabytes each and placed in HDFS. We observe that every block is stored more than once. Actually, it is stored in 3 different data nodes. For example, the first block of the file with the blue color is stored in data nodes 1, 2, and 4. Generally, in distributed systems, we use to have replication of data. If a single machine goes down, we do not want the whole system to collapse, and so does HDFS. Let's now get some hands-on experience on HDFS and see how can we make common file system operations like creating files, deleting files, listing contents of directories on the Hadoop distributed file system. In order to do that, we need to set up a cluster. I have already a setup cluster and Hadoop running on top of it. And what we need to do is to get a terminal, get access on the remote cluster, and play with HDFS. Let's do it. First, I have to get a terminal, and I'm going to connect to the master of the remote cluster. In order to do that, I'm going to use the SSH utility that provides secure connection to a remote machine. So as a first argument, I'm going to put an RSA key that the remote machine needs in order to authenticate me. I need to give my username on that machine and the host name of that machine. And now I'm connected. So in all the operations that we are going to demonstrate on top of HDFS are done with the HDFS utility, but before we do that, let's first check that HDFS actually runs. So I give the JBS utility that will show me all the running Java processes on this system. And here I can see that there is a name node and the secondary name node, which are the Java processes of HDFS that should run on the master. So I suppose that I'm okay. And if I connect to a slave of my cluster and give again JPS, I'm gonna see that a data node runs here, which is the Java process of HDFS in a slave. So again, I suppose that I'm okay. And now let's see how can I inspect the file system. For that purpose, I'm gonna use the command hdfs dfs -ls followed by a path that I want to inspect. The full name of the HDFS path is syntaxed in something like HDFS, the name of the master, followed by port 9000, the default, and then slash, and now I'm going to show and list the contents of the root directory in my HDFS installation. I can see that there are 3 folders, 2 folders actually and 1 file, and I can see the time they have been created, the users that they own them, and their privileges. And we can see that the format it displays information is very similar to the common ls utility of Linux. For example, if I type ls-l and display the contents of a path in my local file system, I get a very similar format. So this is the full name of the prefix that I should put in HDFS paths, but actually, since I have put the HDFS command, that's the default, and I can omit it and get the same result here. So let's see the contents that I have put at this directory. And there is a text file of 260 megabytes, let's say, that contains TripAdvisor reviews. And also another trick here is that the /user/ the username is the default home folder in HDFS, so this is equivalent with typing just this. Okay, now let's say that I want to create another folder within the EESTEC folder, and again I have to type something very similar with the Unix file system and create that one. And if again I inspect the folders, the contents of the EESTech folder, I can see that I just added the folder. And now let's say that I want to go to that place, and let's say that I want to get this file from HDFS and put it locally on my disk here, and practically to download it from HDFS. And in order to do that, I have to do something like this. And get it and put it at the current directory. So I'm waiting a little bit, and now the file should be placed at my local file system. And now let's showcase the reverse procedure. That means to take this file and put it from the local file system, upload it to HDFS, and put it under the new folder. I can do that thing with a command like this. As I run this command, the file, my client reaches the HDFS name node, the file is split into blocks, and the blocks are scattered throughout the data nodes. And now let me check that my file is indeed uploaded at the destination I wanted to. And yes, here it is. And now let's consider that I want to drop this folder and I don't need it anymore. I can delete it by this command, and the folder is deleted. So if I now check again the contents of the EESTEC folder, I can see that only my initial file is here. And also HDFS provides a web UI, and here you can see general information about the cluster. That I have an HDFS cluster that manages 1.3 terabytes of data. There are 3 live nodes that are up and running, and if I go here I can see more detailed information about these nodes. And if I want to browse the file system from the web UI, I have to go to utilities, browse file system, and I have a similar view as in the terminal. So let's continue with our presentation. Okay, let's get back now to the compute layer. Similarly to HDFS, there is a master-slave architecture. The slaves traditionally were called task trackers, and the master is the job tracker. The role of a task tracker is to run map and reduce tasks. In simple words, it provides a running environment for a MapReduce worker. The job tracker is much like a scheduler. It decides on which task tracker a task should be deployed. The Hadoop framework is such that it always tries to ensure data locality. That means that we try to avoid data movements. We do not want a map task that runs on machine A and reads data from a data node running on machine B. The job tracker is also responsible for the fault tolerance of the system. It continuously monitors the deployed tasks it continuously monitors the deployed tasks. In case a task fails or delays its execution more than a threshold, job tracker should reschedule it for execution. The architecture we just described is the one presented in the first half of the picture. We have the clients that issue requests to the job tracker, and it's the job tracker that schedules tasks to the task trackers that actually run the job. However, this was the architecture in the first version of Hadoop. Nowadays, most people use Hadoop version 2, and this newest version is based on the Yarn scheduler and is somewhat more complex. The concepts of Yarn are beyond the scope of this presentation. For now, we can just keep in mind that in Hadoop version 2, the master is called Resource Manager, and the corresponding compute slaves are called node managers. So we have Resource Manager instead of Job Tracker, and node managers instead of task trackers. So let's return to the word count problem. We assume that this is the input file in HDFS. Let's assume that each line of this file comprises a different HDFS block. At the first step, the file is splitted to blocks, and a map task is scheduled for each separate block. Then, the mapper splits lines by space characters, as we know, and computes key values where the key is the word and the value is a unit, i.e. number 1. Each mapper sorts its computed key values and staged them on the local disk of each machine. Then key values are emitted over the network, they are shuffled, and they end up in a bucket. Here, there are the following restrictions. The number of the buckets is the number of reducers we have configured for this job. And the second one, and most important one, is that key values having the same key should end up at the same reducer. So in the first reducer here, we have all the key values that have the bear as key. In the second one, all the key values that have the word car as a key, and so on. Then the reducers combines the partial results. In our example, the reducer which is responsible for the key car sees that there are 3 elements with that key and that have a unit as a value. So it adds up the values and emits a new key value having the same key, that is car, and the sum of the partial frequencies as value. And so it adapts the 3 unit values and computes a value with the number equal to 3. Finally, results of every reducer are written back to HDFS at a path specified by the user. At this point, we should also make the following remark, that the number of deployed mappers here is automatically specified by the input dataset and a splitting strategy. So the user just provides the splitting strategy and the Hadoop framework decides on how many mappers it should deploy. Contrarily, the number of reducers comprises a user-defined parameter. So when we set up a Hadoop job, we should also specify the number of reducers we want to deploy. Let's see now how we can write a program that a Hadoop code that computes the word count on a given dataset. We need 3 Java classes. The first one is the driver. The driver program is, let's say, the main function, the entry point in our code. So in this driver code, we have to specify the paths, the input path and the output path. And we also have to specify which is the class that runs the mapper code and the class that runs the reducer code. Apart from this information, we also provide information on the data types of the keys, of the key values of the output, and also we specify the input and output formats. The input format basically, what it does is that it informs the framework on the splitting strategy that we want to use. Here we use the text input format. The text input format treats a text like key values, where the key is the offset of a line within a file, and the value is the line itself in a plain text format. So the splitting strategy is that we split the file in HDFS blocks, but we also try to ensure that a single sentence and single line is not divided into, it's not splitted into different blocks. If we have a line that is at the end of a block, the block contains the whole line even if it exceeds the HDFS block size. And then we submit the job for execution. Let's go now to see the code for the mapper and the reducer. For the mapper class, we have to extend the Java mapper interface, and we have to pass to give specific information in the generic data types. Here, in general, there are generic types, and we need to give information on what are the types of the input key values: input key, input value, output key, output value. So each mapper gets a key value as input, it transforms it, and it may emit none, one or more key values of that data type. And we have to provide the actual code of the mapper and where computation happens. And in order to provide code for the mapper, we have to implement a function that is called map. It returns void, and it should have exactly the same data types as input key and as input value as they are specified in the prototype of the class. So in our case, we implement just a word count thing where we consider the key is the offset within a file. We do not care about that, but the value is the line that we need to split and parse and count words in it. So we convert it to string, we split it by the space character, and now that we have an array of words, we emit each word as a text and with a value 1, as we have already said. The reason here that we need to convert back the string to the Hadoop text format, text data type, is that in order to write things down to HDFS, Hadoop has first to serialize it. So let's assume that text is a wrapper of strings that offers a serialization method that Hadoop can understand. Similarly, for the reducer code, we have to extend the reducer class, and we have to provide information on, again, for the input and output key values. So here we get as input text and int writable. The mappers provide us with key values that have the word as key and the units 1 as a value. So that's the type of key values that we receive. And we want to make this type of aggregation here, so we want to provide back key values that have, again, a string as a key and, again, an integer number as a value. So again, we give text and int writable. Once again, int writable is a wrapper for the integers that also provides serialization as Hadoop can understand it. And the prototype of the reduce function is, okay, we have the key, and now we have as a value not a single value, but an iterable over values, practically an array of values, because this array is the array of values that share the same key and that we want to reduce to a single one. So we get a key, car, and an array of values, which is this one, in order to reduce it to the sum in the case of word count. So for each separate key, let's say car, we initialize a counter and we'll iterate over all available values from the key values that have reached the same reducer, and we compute the sum out of them, and finally emit the key with the final frequency that it appears on the text. And that ends up to be written on HDFS. That's all. So another question here is how we can decide that bear ends up at this reducer and car at this one, and they are not grouped together with a different way. For this reason, there is the concept of partitioner. The partitioner provides the logic with which shuffling happens. So we have a mapper to emit different key values. We have a given number of reducers, and we want to determine which keys should end up at which reducer. So how can we do that? The Hadoop framework provides a class named Partitioner. So if we want to provide a specific logic for the sampling, we just have to extend the Partitioner class. In our case, the partitioner for the partitioner, we also need to specify the generics that represent the key value that are emitted from the mapper. So in our case, this is text and int writable. Okay, and in order to provide the logic, we have to implement the getPartition function that gets each key value as input and does output, and the number of reducers, here that the number of partitions is the number of reducers. In our case, in our example here, this is 3. And we have to provide a logic that returns an integer number. This integer number is the ID of the reducer. So if here the result is 0, the key value would end up at the first reducer. If the result is 1, the key value would end up at the second reducer, and if the result is 2, the key value would end up at the third reducer. What we do at this example is that for a given key, we compute its hash code, and we take the modulo of this hash code with the number of reducers. So basically, we assign randomly each key to a different reducer, but as same keys produce the same hash code, for example, 2 key values that both have the car as a key would produce the same hash code, we guarantee this way that these key values would end up to the same reducer. So, something that is interesting here is that the implementation of a partitioner can have great impact on performance, because if, let's say, that our partition logic for some reason is biased and most times returns 0, then most of these key values would end up at the first reducer. What's the problem here? The problem is that since the first reducer has received many key values, it has a lot of work to do, while the other 2 reducers are almost idle. So here we cannot exploit the parallelism. We have 2 or 3 machines that are idle and do nothing, and 1 machine that is struggling. So the ideal situation would be something like this. We want our keys to be as equally distributed as possible. We want every reducer to have to receive almost the same amount of keys. So we want to be careful on the designing of the partitioning strategy in order to guarantee balanced partitions. Another optimization that we can do and that the Hadoop framework supports is the concept of combiner. The way we implemented our word count in Hadoop is that every time that we emit a specific word, let's say the word car, we emit a key value that has as key the word itself, let's say car, and as value the unit. So at this block, we emit the key value car, comma, 1 2 times. The first time I emit this key value, the second time I emit this key value. The problem with that is that we emit and we transfer over the network redundant amount of information, and we create network bottlenecks when there is no reason to do that. So the idea of combiner is we can think of combiner as a map side reducer. So after the key values are created, we could reduce them at the map side before we transfer them over the network, and this thing would be transformed to a key value with the key with car as the key and the number 2 as the value. So at that case, we would transfer over the network half the amount of information we transferred in the naive case. And the implementation of combiner is that we extend again the reducer class, so it's actually exactly the same code with the reducer that we presented before. It's a reducer that we need to implement, and we go at the driver program and we add this line. We say that the job has to contain this code, the combiner class, as a combiner. Once again, we are going to connect to the remote cluster where Hadoop is set up, and we are going to run the word count application and see how we can run such a program in practice. So let me get a terminal. I use SSH to connect as before. Okay. I go to this folder in my system where I have a jar file that contains all the code that we just saw in the slides. So let me first check that Hadoop is running. I run the JPS command that we saw and in the HDFS demo, and I can see that in the master the resource manager is running, so I know that the master of Hadoop is up. I can also check in a slave, and if I run JPS here, I can see that node manager is running, which is the container of my worker, let's say. So I'm good. Now I can also check the UI of the application, which can be accessed at the master IP. So here I can see my cluster. It's a cluster where there are 3 active workers. It has 24 cores in total and 24 gigabytes of main memory. So let's submit our application. In order to submit a Hadoop application, I can run use the yarn utility, and I write yarn jar, the name of my jar, and then I need to specify which class of this jar should run. So I write the package name and the class name. Followed, my code now takes two arguments. One, we saw that one argument is the input. We saw that, we saw that here, the input and the output. So let me for now give wrong arguments. Okay, input path does not exist. Let's find our input. I use the HDFS command, as we learned, and I inspect the EESTEC folder. So let's give this file as an input. So I go here, and as input, I give the EESTEC and as output, under the EESTEC folder, let's create the trip out folder, and I run again my application. Okay, we can see that there is one input path to process, and according to the splitting strategy, this path is split in 4 blocks. So there would be 4 mappers that are going to be deployed and process my WordCount application. Now, if I go to the UI, I can see that there is one submitted application with that ID of that user. That's the jar file that runs. The type of application is MapReduce, and I can also see the resources that are utilized right now. So I have I have deployed containers that use 5 cores and 10 GB of memory. Here we can see also the progress of the application, both for the maps phase and the reduce phase. And the application completed successfully. And at the end of the application, we can also see some metrics like how many input records did I receive, how many output records, how many combined records, reduced records, and so on. And that's the Hadoop demo. Let's go back to our presentation. Okay, so this is Hadoop, and everything is really fine with Hadoop, except one thing. We go to the disk subsystem very often. That means that, okay, initially data are located in HDFS, so we need to access both disk and many times network. We make the map, we run the map phase, mappers compute their outputs, and then again mappers have to stage intermediate results on their local disks and then send them over the network and run the reduce phase, and reducers again have to run things on disk. So if I have an algorithm that needs to make many iterations and the data is that big that I need to run a MapReduce job for every iteration, then the I/O is too much. I have to go to the disk or network very often, and that's an overkill. So we cannot afford that many disk accesses. And that's where the Apache Spark comes to the rescue. So what Spark provides and beats Hadoop is that instead of going to the disk that often, we can stage intermediate results in a distributed memory thing and not going to the disk subsystem that often. Okay, so Spark is a newer project than Hadoop, and it has the Spark core layer that provides the programming model that supports both MapReduce and other frameworks beyond MapReduce. Spark code is not restricted only to MapReduce cases. The Spark core layer can run on top of many known both databases and file systems, so we can have Spark running on top of HDFS or on top of a database or on top of a local file system. And there are also a lot of work that has been done to extend Spark and create libraries that provide ready code for many different tasks. So except of writing native Spark code, we can use libraries that provide SQL utilities, so we can make SQL queries and run analytics jobs on top of Spark without having to implement everything from scratch. We can just write SQL clauses, and this SQL translates behind the scenes to Spark code. We can use the Spark streaming and handle streaming scenarios, and Spark also provides libraries for dealing with machine learning problems or graph problems, and all this work that has been done by the community gives us great flexibility and convenience to tackle modern problems on real-life data. And also, on top of these languages, we can see another layer of the language APIs that Spark exposes. And in contrast to Hadoop, that we are restricted mainly to Java and we mainly write Java code, the Apache Spark project provides 4 interfaces. There is a Scala interface, a Java interface, a Python, and an R interface. So we can write code in any of these 4 languages, and behind the scenes, this code triggers native Spark code that gives us great performance. In the WordCount example here, I have used the Scala interface, and the reason I chose Scala as a language for my example is that mainly in the web, if you try to find code for many different tasks, the most commonly used language for Spark is Scala. So it's more easier, it's more well documented, and it's more easier to find resources for code, for Spark code that is written based on Scala. So we said before that the reason Spark became that popular is because it can provide this distributed memory abstraction. But how it does it, how it can achieve such a thing? And the answer is with a structure called resilient distributed datasets, or simpler, RDD. An RDD is an immutable distributed collection of objects. So imagine that is a list with many objects, and we cannot modify this list. And this list, as it represents the whole dataset, and we talk about big data, we can consider it as being divided into logical partitions, in a similar way that we divide a Hadoop file in HDFS blocks. So I have my data, and this data is partitioned on many partitions. Okay, so the thing is that RDD is implemented in such a way that this collection of objects can be persistent in memory, or at least as many partitions are as they fit in the aggregate memory of my cluster. So how can I create an RDD? There are two ways. The first way is that my driver code has in memory a collection, let's say a list, and I can parallelize it and say that, okay, the list that you have in memory now, split it in different partitions and spread it across the cluster. The second way is to reference a dataset in an external storage system. That means that I can read an HDFS file, or I can read the database table and load it as an RDD. That means load it, split it, and spread it across the cluster. So now my dataset is moved from the external storage system to the main memory of all the nodes of my cluster. What can I do with an RDD? So I have the RDD in memory. How can I handle it? How can I make different operations with it? RDD operations are split into categories. The first category is called transformations. Transformations are evaluated in a lazy way. That means that when I make a transformation, the Spark framework does not compute everything, returns immediately, there is no latency in that operation, and it goes on with the code. Actions trigger transformations. That means that if I have two transformations and one action, there is no latency in make any of the transformations, but when the code meets the action, both the transformations and the action are actually computed. Let's see it in practice. That's the word count code for Spark. That is exactly what we did for Hadoop, and in the functional way of writing of Scala, we can write it in 5 lines of code. So let's see what does this code do. In the first line, we have an HDFS path, and we want to load the dataset that exists in that path as an RDD in the memory of the cluster. So that command loads the dataset that exists at that path as an RDD. And as such, text file from now on is an RDD. We can handle it as an RDD. Next, as we have this RDD, we want to perform the well-known word count operations. That is that we want to split the lines of the text and emit key values in the form of word as a key, the unit as a value, and then we want to reduce partial results as we did before. So here we take the RDD and we call the flat map operation that takes each element of the input, that each line of the text, and applies a function on that line. The function we have specified is the splitting by the space character. So we get the line, we split it, and the flat map returns as output a list with the results of that splitting. So the output of that line would be a list of the words existing in that line. The flat map operation is a transformation. That means that when the code reaches that point, it sees that we have a transformation here and goes on without computing anything. Then we meet the map function. The map function gets each word that is emitted from the flat map and applies another function on it and gets a word and returns a tuple in the format that we already know. The map operation is again a transformation. So as the code reaches at that point, again it does not compute anything and goes on. Then we meet the reduce by key operation. That pretty weird syntax wants to say that when you get two tuples that have the same key, just add the values and return a tuple with the same key and the sum of the values. And also this reduce by key operation includes in its implementation a combiner, so that we could say that that's a pretty good one. And again, the reduce by key is a transformation, so when the code reaches that point, we have a counts object that is an RDD, but nothing of these things has really run and no computation has happened. And then we want to save this RDD on disk, and we call the save as text file operation, and we give a destination path at HDFS. As the save as text file operation is an action, now the whole code of these lines is triggered, and now is that the actual computation begins. And as we call the save as text file method, is that Spark begins to actually run the flat map, the map, the reduce by key, and finally the save operation on disk. We are now going to dive deeper in Spark computation. Spark perceives each set of operations as a directed acyclic graph. So there is a DAG scheduler component that runs in the master node and is responsible for the task scheduling. The scheduler partitions the DAG into stages. A different stage is created every time a shuffling operation takes place. For example, in our case here, the reduce by key operation, which includes shuffling, initiates the creation of stage 1. As within a stage there are no dependencies with other partitions, tasks can run fully in parallel. As in the Hadoop case, a different task is created for every RDD partition. Let's now run a word count example on Spark and see the last demo of our presentation. Once again, I need to connect to the cluster, so I get the terminal. I'm connecting, I check, and there is no Spark running, so I have to start Spark. We can see the log messages that show that master and workers are starting. Now I'm ready, and I'll run my example on the interactive shell of Spark, so I'm initializing the Spark shell. Okay, so now I have a Spark shell. So I want first to load as an RDD my text file. Sorry, text file. Okay. Now I have to provide the HDFS path, which should be a complete path with the HDFS prefix, the name of the master, port 9000, and then let me remind myself the name of the file that we used in the previous example. Okay, that's it. All right. An RDD of strings is created, and now I'm going to compute the frequencies. Flat map, I want to take a line and return this line split by spaces, and then map each word to a tuple with that word as a key and the unit as a value. And finally, I want to reduce by key these tuples and reduce them by adding up the corresponding frequencies. And now, by hitting the enter key, that returns almost immediately without having actually performed all these computations. And now I'm going to trigger the action and save this file at HDFS at this path. Okay, let's put it here. And now you're going to see that when I will strike the enter key, then actual Spark computations are going to be triggered. So I hit, oh, sorry, that's not counts, this is count. And we see that now the first stage is starting to be computed, and if we go to the web interface, we can see the operation, we can see many statistics, see the computed thing, and that's all. So going back to our presentation, that was a Hadoop and Spark introduction. You can find much more information on both frameworks on the official documentation sites that these are here. This is a very complete book that I recommend for Hadoop and its internals, and this is another reference that I would also recommend, and it's a little bit more theoretical and is on designing MapReduce algorithms and not examining the thing from the system aspect. And always remember that Google is your best friend. And thank you very much, and I'll be happy to receive any question at this email. I remind it is jimmy.til@syslab.ec.ntua.gr. Thank you very much.
As Mr. Mytilinis told you, send us your questions via email on these email addresses. We will, with help from Mr. Mytilinis and EESTech Challenge Academic Supervisor, Dr. Constantinou, answer all your questions. Follow our social media in order you to be informed for our next moves, the next seminars, the webinars that we will propose you to watch. On behalf of EESTech Challenge Board, I would like to thank Mr. Mytilinis for this awesome and very interesting presentation. At the same time, I would like to thank all of you for attending. And don't forget that EESTech Challenge rocks. Are you ready for this challenge? Good night.